February 24, 1944, Anzio beachhead, Italy. Lieutenant Werner Hoffmann watched from his captured observation post as darkness fell across the contested shoreline. For 3 weeks, Luftwaffe bombers had pounded Allied positions with near impunity. German artillery observers radioed coordinates. Heinkel bombers approached at low altitude. Anti-aircraft fire bloomed uselessly in the empty sky. Then, something changed. The familiar rhythm of defensive fire acquired an unfamiliar precision. Shells detonated exactly where bombers would be, not where they had been. 7 Heinkels entered the beachhead airspace that night. 7 Heinkels disappeared in perfectly timed explosions. Hoffmann had observed Allied anti-aircraft operations in North Africa. He understood British gunnery procedures, knew American defensive doctrine. Nothing in his training explained what he witnessed. The shells anticipated aircraft movements with accuracy that optical directors could not achieve under complete darkness. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. 3 months later, Hauptmann Klaus Richter stood in a muddy field outside Saint-Lô, France, examining equipment that would shatter every assumption German radar engineers had maintained about American technical capabilities. The captured SCR-584 system looked ordinary enough at first glance. A 6-foot dish antenna mounted on a trailer, standard military electronics housing, nothing that suggested revolutionary capability. But when Richter powered up the American radar for the first time, his professional confidence began its inexorable collapse. The automatic tracking engaged smoothly, following targets with mechanical precision that exceeded anything Würzburg systems could achieve. Range accuracy, measured in meters rather than the tens of meters his equipment required. Most disturbing of all, the Prodent entire system fit on a single trailer, while equivalent German radar installations required multiple vehicles and extensive setup procedures. In that moment, surrounded by the hum of American servo motors and the glow of cathode ray displays, Richter realized the terrible truth German high command had missed. The Americans weren't just building better radars, they were fighting an entirely different war, one where mathematics and automation had transformed ordinary weapons into instruments of devastating precision. The SCR-584 held the secret to why German anti-aircraft batteries kept failing despite superior gun caliber and explosive power. The mathematics had shifted beneath their feet, and Germany had never noticed until it was far too late. The story began 5 years earlier, in a London already bracing for war. September 1940, the Tizard mission arrived in Washington, carrying Britain's most closely guarded technical secrets, wrapped in diplomatic pouches and locked metal cases. Among the delegation, physicist Edward Bowen carried something that would revolutionize warfare, though the Americans didn't know it yet. The initial meetings proceeded with diplomatic caution. British scientists hesitated to reveal technological advantages without receiving equivalent information in return. American military brass listened politely to discussions of radar development, unimpressed by what seemed like incremental improvements to systems they were already building. Then Bowen produced a small device from a metal box. The cavity magnetron, barely larger than a man's fist, represented 5 years of concentrated British research compressed into a few pounds of precisely machined copper and steel. American radar expert Lee Dubridge examined the device with growing astonishment as Bowen explained its capabilities. The magnetron generated microwave radiation at 10 centimeter wavelengths, with power output that exceeded American long-wave radars, despite being thousands of times smaller. One American historian would later describe it as the most valuable cargo ever brought to our shores. The potential was immediately obvious to anyone who understood electromagnetic propagation. Short wavelengths meant tight beam focus. Tight beams meant precise, angular resolution. Precise resolution meant accurate target tracking. Accurate tracking meant effective fire control. The entire logical chain led to one conclusion. The cavity magnetron made radar-directed anti-aircraft fire theoretically possible for the first time in history. Within weeks of the Tizard mission's revelation, Vannevar Bush established the MIT Radiation Laboratory in Cambridge, Massachusetts. The facility opened in December 1940 with a specific mandate: Develop microwave radar systems that could track aircraft with sufficient precision to direct anti-aircraft guns in real time. The challenge seemed insurmountable by every conventional engineering measure. Radar sets required stable platforms and careful calibration to achieve useful accuracy. Anti-aircraft guns operated in field conditions with vibration, temperature extremes, and combat stress that destroyed delicate equipment. Combining the two technologies meant solving problems that touched every discipline of electrical and mechanical engineering simultaneously. Alfred Loomis, directing the Radiation Laboratory's microwave research, advocated for an approach that conventional military thinking considered dangerously radical. Complete automation of the tracking process using servo mechanisms and feedback control systems. No human operators adjusting antenna positions. No manual calculations of target trajectories. Just electronics sensing target position and motors responding automatically to maintain lock. Military brass initially dismissed the concept as academic fantasy. Servo systems were delicate laboratory devices, not battlefield equipment. Feedback control required precision machining that field. Conditions would destroy within hours. The idea of building a radar that could track high-speed aircraft automatically while mounted on a trailer that could be towed behind a truck violated every principle of military equipment design they understood. But Loomis possessed something his critics lacked: an intimate understanding of the mathematical principles that governed both radar propagation and servo control systems. He knew that conical scanning could provide tracking information precise enough to direct guns, if the mechanical systems could respond fast enough. He also knew that American industrial capacity could manufacture precision components at scales German factories could only dream of attempting. The development program proceeded with wartime urgency that eliminated normal bureaucratic delays. Engineers worked 18-hour days, solving problems that had never been confronted before. How do you build vacuum tubes rugged enough to survive field transportation but sensitive enough to detect faint radar returns? How do you design servo motors powerful enough to swing a 6-foot dish antenna, yet precise enough to track targets moving hundreds of miles per hour? Ivan Getting led the radar development team with methodical precision. The conical scanning system he designed represented sophisticated understanding of electromagnetic wave behavior. A single feed horn mounted slightly off the antenna's center axis rotated at 25 revolutions per second. As it spun, the radar beam swept a narrow cone through space, creating a scanning pattern that revealed target position with extraordinary accuracy. When the beam center pointed directly at a target, the return signal strength remained constant throughout the rotation. But if the antenna aimed even slightly off target, the signal varied as the scanning pattern swept across the target's position. Electronics detected this variation and generated error signals that drove servo motors to correct the pointing angle automatically. The system achieved angular accuracy better than 1/10 of a degree, precise enough to direct guns against targets 40 miles distant. Maximum detection range reached 65 kilometers against large bomber aircraft. Range accuracy measured 75 feet at maximum distance, allowing precise calculation of future target position. But the radiation laboratory developed only half the complete fire control system. Converting radar data into gun-laying solutions required a separate analog computer that could calculate complex ballistic trajectories in real time while accounting for dozens of variables that affected shell flight. Bell Telephone Laboratories received the contract to develop the fire control computer in December 1940. The specifications demanded capabilities that pushed analog computing technology to its absolute limits. Calculate target course and speed from radar position updates. Predict future target location, accounting for acceleration and maneuvering. Compute shell ballistic trajectory, including effects of air density, wind speed, powder temperature, and Earth's rotation. Generate continuous pointing commands for up to 4 90mm guns simultaneously. David Parkinson led the Bell Labs development team after allegedly conceiving the basic design in a dream where he observed anti-aircraft crews operating equipment that didn't yet exist. Whether the story was literal truth or convenient mythology, Parkinson's analog computer design proved revolutionary. The M9 gun director contained more than 2,000 precision components arranged in functional blocks that performed specific mathematical operations. Potentiometers acted as variable resistors programmed by turning calibrated dials. Servo motors positioned mechanical linkages that represented mathematical relationships. The entire assembly performed continuous trigonometric calculations at speeds human operators could never match. Electrical. Inputs from the SCR-584 radar entered the M9 through synchro motors that converted antenna position into mechanical shaft angles. Additional inputs came from manually set dials that operators adjusted for munition type, local barometric pressure, and wind conditions. The computer processed all inputs simultaneously, generating output signals that drove servo motors on the gun mounts. Once the system locked onto a target, gun crews needed only to load ammunition. The M9 calculated where the target would be when shells arrived, led the guns to the proper angles automatically, and maintained tracking as aircraft maneuvered through evasive action. Human reaction time had been eliminated from the fire control loop entirely. The complete system, SCR-584 radar paired with M9 director, was demonstrated on April 1, 1942 at Fort Monroe, Virginia. Military observers watched as the equipment tracked aircraft with precision that exceeded manual optical directors even under perfect visibility conditions. Angular errors measured in fractions of a degree. Tracking remained smooth despite aircraft performing violent evasive maneuvers. The Army ordered 1,256 complete systems the following day. Production presented challenges that matched development complexity. The SCR-584 required precision machining of the 6-foot parabolic antenna, careful assembly of hundreds of electronic components, and exacting calibration of servo systems. Chrysler Corporation's Dodge division received the manufacturing contract and transformed their Detroit facilities into radar production lines practically overnight. By August 1943, Chrysler had delivered 610 complete SCR-584 systems, with production accelerating toward eventual total output of over 1,700 units. The M9 gun director proved even more complex to manufacture, requiring Bell Labs to coordinate production across multiple subcontractors who specialized in precision mechanical assemblies. But while American factories churned out radar-directed fire control systems by the hundreds, German anti-aircraft defenses relied on equipment designed according to fundamentally different philosophical principles. The Würzburg radar represented German technical sophistication at its finest. Developed by Telefunken starting in 1935, it used conical scanning similar to the American system and achieved respectable performance within its design parameters. The standard Würzburg A featured a 3-meter dish antenna that provided reasonable angular accuracy at 50 centimeter operating wavelength. The range extended to approximately 30 kilometers against aircraft targets. Angular accuracy reached roughly 1 degree under optimal conditions. The Würzburg Riese, introduced in 1941, used a massive 7.5-meter dish that improved both range and resolution, extending effective tracking to 70 kilometers with improved precision. But German fire control doctrine assumed human operators would convert radar data into gun-laying solutions using optical directors and mechanical calculators. The Würzburg provided target position information. Separate crews operated searchlights that illuminated targets for visual tracking. Gunlayers adjusted their weapons based on shouted commands from fire control officers who calculated trajectories using tables and slide rules. The system worked adequately against slow-moving bomber formations, flying predictable courses. Experienced crews could engage targets effectively under good visibility conditions, but darkness, weather, and high-speed maneuvering aircraft degraded performance catastrophically. Human operators simply could not process information fast enough to maintain accurate tracking against targets that crossed engagement zones in seconds rather than minutes. More critically, German radar doctrine emphasized early warning and fighter direction over direct gun laying. Würzburg systems detected incoming raids and vectored night fighters to interception positions. The radars provided approximate target locations, but final engagement depended on pilot skill and luck rather than mathematical precision. American doctrine eliminated luck from the equation entirely. The SCR-584 and M9 transformed anti-aircraft fire into a mathematical certainty. Targets within range would be tracked automatically. Guns would be laid with precision that optical directors could never achieve. Shells would arrive at predicted intercept points with accuracy measured in meters rather than hundreds of meters. The philosophical difference reflected deeper contrasts between American and German approaches to military technology. German engineers built sophisticated equipment that required highly trained specialists to operate effectively. Complex systems assumed peacetime maintenance conditions and technical expertise that became increasingly scarce as the war progressed. American engineers built equipment that ordinary soldiers could operate after minimal training. Simplicity and reliability trumped theoretical performance. Components were designed for field repair using standard tools. Entire systems fit on mobile trailers that could be deployed rapidly without extensive site preparation. The first combat deployment of the complete SCR-584 and M9 system occurred at Anzio in February 1944, though bureaucratic delays had prevented earlier battlefield use despite systems being production-ready months earlier. 2 complete radar-directed fire control batteries arrived at the embattled beachhead just as Luftwaffe bombers intensified their attacks on the confined Allied perimeter. The German air offensive had achieved devastating effectiveness during previous weeks. Allied anti-aircraft guns fired desperately at targets they could barely track in darkness. Shells exploded harmlessly while bombers completed their runs unopposed, dropping high explosives on ammunition dumps and supply ships with systematic precision. Then the SCR-584 systems became operational. The first night engagement demonstrated capabilities that shocked both Allied and German observers. Radar locked onto incoming bombers at maximum range. The M9 calculated interception trajectories automatically. 90mm guns traversed smoothly to predicted firing positions. Shells detonated exactly where mathematics dictated they should, creating lethal fragmentation patterns that German pilots could not evade through speed or maneuvering. 7 Luftwaffe bombers entered the engagement zone that first night. 7 bombers disappeared in precisely timed explosions. The attacks ceased for a week, while German air commanders attempted to understand what had transformed Allied defences from ineffective desperation into mathematical precision. A single reconnaissance bomber probed the beachhead defences a week later. It was destroyed within minutes of entering radar range. Luftwaffe attacks on Anzio effectively ended as German commanders recognized that daylight or darkness made no difference to American fire control accuracy. The mathematics of radar-directed guns had rendered conventional bombing tactics suicidal. The captured SCR-584 arrived at the German Army testing facility at Kummersdorf in late June 1944. Hauptmann Klaus Richter received orders to conduct a complete technical evaluation of the American radar system with unusual urgency. Wehrmacht intelligence had intercepted reports describing devastating anti-aircraft effectiveness that conventional German doctrine could not explain. Allied guns were achieving hit rates that seemed impossible without some revolutionary fire control breakthrough. Richter approached the examination with professional skepticism born from 3 years evaluating captured enemy equipment. British radar systems had proven competent, but unexceptional. Soviet technology lagged far behind German standards. American equipment typically emphasized mass production over technical sophistication, creating weapons that worked adequately without achieving excellence. The SCR-584 challenged every assumption within minutes of initial inspection. The antenna mount incorporated precision bearings and servo motors that allowed rapid slewing with minimal vibration. The 6-foot parabolic dish had been stamped from sheet steel rather than individually machined, yet maintained surface accuracy within tolerances that German fabrication techniques achieved only through expensive hand finishing. Most remarkable was the integration. The entire radar system, including transmitter, receiver, antenna mount, and tracking servos, occupied a single trailer that could be towed behind a standard truck, no separate generator vehicles. No auxiliary equipment trailers, just one self-contained unit that 2 soldiers could deploy in under an hour. Richter's Würzburg installations required multiple vehicles, extensive cabling, careful leveling procedures, and calibration that consumed hours, even with experienced crews. The American system apparently assumed field conditions would be chaotic and designed accordingly. Simplicity defeated sophistication through ruthless focus on battlefield practicality. The conical scanning system impressed Richter despite his initial resistance to acknowledging American technical achievements. The offset feed horn rotated smoothly at 25 cycles per second, driven by a motor whose precision rivaled laboratory equipment. Electronics separated the scanning signal from target returns with elegant efficiency, generating error voltages that drove the tracking servos with response times measured in milliseconds. German Würzburg systems used similar conical scanning principles, but implementation revealed telling differences. The Würzburg quirk rotated at the same frequency but required careful maintenance to prevent mechanical wobble that degraded tracking accuracy. American engineering apparently accepted that field personnel would perform minimal maintenance, so the system was designed to maintain precision despite neglect and rough handling. Oberst Heinrich Müller joined the evaluation on the second day, bringing combat experience that complemented Richter's technical expertise. Müller had commanded flak batteries through the Battle of Britain and North African campaigns, accumulating enough battlefield observations to recognize the tactical implications of superior fire control. The range accuracy troubled Müller most profoundly. The SCR 584 technical manual claimed a range precision of 23 meters at 40 kilometers. Müller's Würzburg experience suggested such accuracy was theoretically possible, but practically unattainable under field conditions. Atmospheric refraction, equipment calibration drift, and operator error combined to degrade real-world performance far below laboratory specifications. Yet the ANZIO combat reports documented hit rates that required exactly the precision the Americans claimed. German bombers had been intercepted at ranges where Würzburg tracking became unreliable. Shells had detonated at predicted positions despite darkness and weather that rendered optical directors completely useless. The mathematics supported only one conclusion: the American system actually achieved its claimed performance under combat conditions. Richter activated the automatic tracking mode and immediately understood why American anti-aircraft batteries fought with superior coordination. Once the radar locked onto a target, servo motors maintained pointing with mechanical precision that human operators could never match. No fatigue, no distraction, no gradual degradation of performance as battles extended through hours of continuous engagement. The system tracked a test aircraft with smooth efficiency that made Müller wince with professional recognition. His best Würzburg crews could maintain comparable accuracy for perhaps 10 or 15 minutes before fatigue degraded their performance. The American equipment would track indefinitely with identical precision whether the engagement lasted seconds or hours. The height-finding capability particularly impressed both evaluators. The SCR 584 measured target elevation angle with the same precision it measured azimuth, providing complete three-dimensional position data from a single rotating antenna. German practice typically paired Würzburg azimuth radars with separate height-finding equipment, creating coordination problems and information delays that limited fire control effectiveness. American integration eliminated these problems entirely. One radar provided all necessary tracking data simultaneously. One set of servo outputs drove the gun director. Information flowed continuously from target to weapons without human processing delays or coordination bottlenecks. But the deepest revelation came when Richter examined the technical manual's fire control integration specifications. The SCR 584 was designed from inception to work with an automatic gun director that converted radar position data into firing solutions without human intervention. The entire system assumed that electronics and servo motors would replace human decision-making in the fire control loop. German doctrine assumed humans would interpret radar data and make tactical decisions based on training and experience. American doctrine assumed mathematics would make those decisions faster and more accurately than any human could achieve. The philosophical gap was unbridgeable through equipment modifications alone. It required fundamentally different thinking about how technology should support warfare. Mueller requested additional documentation about the American gun director system. Intelligence reports mentioned an M9 analog computer built by Bell Telephone Laboratories, but German analysts had dismissed it as typical American overcomplication. Mechanical calculators like the Sperry M7 provided adequate fire control for existing doctrine. Electronic computers seemed like an unnecessary expense for marginal improvement. The Anzio combat results proved that assessment catastrophically wrong. 7 bombers destroyed in a single engagement, near-perfect tracking accuracy under complete darkness, hit rates that suggested shells were detonating exactly where mathematical prediction indicated they should. These outcomes required fire control precision that mechanical calculators could not provide. Richter calculated the mathematical requirements for the observed performance. Tracking a bomber at 400 km per hour required position updates at least 10 times per second to maintain smooth servo response. Each update had to account for target acceleration, atmospheric conditions, and ballistic trajectory calculations that included dozens of variables. The computational load exceeded what mechanical calculators could handle by orders of magnitude. An electronic analog computer could perform these calculations continuously in real time, generating output signals that drove gun servos directly without human intervention. The computational speed would be limited only by electronic response times, allowing tracking of targets whose maneuvers exceeded human reaction capabilities. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The third day of evaluation brought Oberst Werner Brandt from Luftwaffe Intelligence with specific questions about V1 flying bomb vulnerability. The pilotless missiles had begun striking London in mid-June, achieving a devastating psychological impact that Hitler hoped would break British morale and disrupt Allied invasion support. Initial defensive responses had been encouraging from the German perspective. British fighters struggled to intercept the fast, low-flying missiles. Anti-aircraft guns achieved hit rates below 20% during the first weeks of the campaign. The V1 seemed to exploit weaknesses in conventional air defence that would allow sustained bombardment of London despite Allied air superiority. Then American SCR-584 radars and M9 directors arrived in England, deployed specifically against the V1 threat. Within 6 weeks, British anti-aircraft hit rates jumped from 17% to 74%. The transformation was so dramatic that Luftwaffe intelligence initially suspected the statistics were propaganda designed to demoralize German forces. But reconnaissance confirmed the numbers. V1 wreckage littered the English coast in quantities that matched British claims. The flying bombs were being destroyed at rates that made the entire campaign tactically futile. Hitler's vengeance weapon had been neutralized by American fire control technology that converted near-certain success into near-certain failure. Brandt examined the SCR-584's tracking specifications with growing dismay. The V1 flew straight and level at consistent altitude, presenting the ideal target for automatic tracking systems. Once the radar locked on, the missile's predictable trajectory allowed the M9 director to calculate interception with minimal uncertainty. Guns could be laid with confidence that shells would detonate exactly where the V1 would be when they arrived. German anti-aircraft doctrine provided no countermeasures against this level of fire control precision. Evasive maneuvering was impossible for the pilotless missile. Speed variations would disrupt the guidance system's timing mechanism. Flying higher reduced bombing accuracy unacceptably. The V1's design assumptions had been invalidated by technology that converted its predictability from advantage into fatal vulnerability. Richter shared calculations that painted an even grimmer picture. If American production achieved the scale that intelligence reports suggested, the Allies could deploy hundreds of SCR-584 systems across Europe within months. Every major anti-aircraft installation could receive radar-directed fire control that would render daylight bombing by conventional aircraft nearly suicidal. German air superiority, already eroded by numerical disadvantages and fuel shortages, would collapse entirely against defenses that combined American fighter numbers with mathematically precise anti-aircraft fire. The Luftwaffe would be forced to abandon daylight operations completely, or accept casualty rates that would exhaust trained aircrew within weeks. Müller's tactical experience provided the final piece of devastating analysis. German anti-aircraft batteries had consistently outperformed Allied guns throughout the war, despite being outnumbered. Superior German optical directors and well-trained crews achieved better hit rates under comparable conditions. That performance advantage was the only factor preventing Allied air forces from achieving complete operational freedom. The SCR 584 and M9 eliminated German fire control superiority through automation that required minimal crew training. American batteries manned by soldiers with weeks of instruction could achieve accuracy that German crews required years of experience to match. The force multiplication effect was catastrophic. Every American gun became equivalent to 3 or 4 German weapons in terms of effective firepower. Worse, the American system's reliability meant that performance remained consistent, regardless of crew fatigue, combat stress, or environmental conditions. German optical directors degraded rapidly under poor visibility. Trained crews became casualties and were replaced with inexperienced personnel whose performance was mediocre at best. American automation converted adequate soldiers into effective operators through technology that absorbed the skill requirement. The evaluation concluded after 5 days of intensive testing and analysis. Richter compiled a technical report that documented American superiority with scientific precision. The SCR 584 outperformed Würzburg systems in every measurable category while requiring less maintenance, fewer operators, and simpler deployment procedures. Combined with the M9 gun director, it created fire control capabilities that German technology could not match given existing industrial capacity and time constraints. But the report's strategic implications extended far beyond technical comparisons. American industrial philosophy had created weapons systems that ordinary soldiers could employ effectively under combat conditions. German industrial philosophy had created sophisticated equipment that required specialist operators and ideal maintenance conditions. The difference was determining battlefield outcomes through accumulated tactical advantages that would shape the war's final resolution. Müller forwarded the report to Berlin with a cover memorandum that the Wehrmacht leadership found too pessimistic to accept. He calculated that American radar-directed anti-aircraft fire would increase defensive effectiveness by a factor of 3 to 4 compared to German systems. If proximity-fused ammunition was added to the equation, the multiplier could reach 5 or 6. Such improvements would make Allied air defenses impenetrable to conventional German aircraft. Strategic bombing of British targets would become impossible. Tactical air support for Wehrmacht ground forces would be suppressed completely. The Luftwaffe would be forced into purely defensive operations, ceding air superiority to Allied forces, whose numerical advantages already approached overwhelming. The mathematics were inexorable, and Müller had learned through bitter experience that mathematics determined tactical outcomes regardless of courage or determination. German forces could fight with skill and dedication, but they could not overcome systematic disadvantages that multiplied Allied effectiveness while degrading German capabilities. The summer of 1944 demonstrated the accuracy of Müller's predictions with brutal clarity. American SCR 584 systems deployed across France following the Normandy invasion, providing air defense for advancing Allied forces. German aircraft attempting to attack invasion beaches encountered anti-aircraft fire that tracked them with precision that darkness and weather could not degrade. Luftwaffe losses mounted steadily as American fire control transformed the tactical equation. Missions that previously involved acceptable risk became near-certain suicide. German pilots reported that American guns seemed to anticipate their every maneuver, placing shells exactly where evasive action would take them rather than where they currently flew. The reports described reality accurately, though German aircrew could not know the mathematical principles underlying their torment. The M9 director calculated not just current target position, but predicted future location based on observed velocity and acceleration. Guns were laid to intercept the target's projected path, rather than its present position. Pilots who maneuvered to avoid predicted fire simply flew into shells that had been aimed at where their evasive action would take them. By August, the V-1 flying bomb campaign had collapsed under the devastating effectiveness of SCR-584 directed anti-aircraft fire. On August 28, 104 Von-Second were launched against London in Hitler's final attempt to break British morale through sustained bombardment. British radar-directed guns destroyed 64 missiles. Fighters accounted for 14 more. Only 4 Von-Second reached London, the remainder having crashed due to mechanical failures or guidance errors. The campaign that Hitler had expected to terrorize Britain into negotiation had achieved nothing except demonstrating American technological superiority. Over 1,600 Von-Second had been destroyed by anti-aircraft fire alone, roughly matching fighter kill totals despite guns being restricted to coastal defense zones. The SCR-584 had proven itself the most effective ground-based air defense system deployed by any combatant during the entire war. German radar engineers studied every scrap of intelligence regarding American fire control systems, searching for weaknesses that could be exploited or countermeasures that could reduce effectiveness. The analysis revealed uncomfortable truths about industrial capacity and design philosophy that extended far beyond radar technology. American systems emphasized reliability over theoretical performance. Components were designed for field repair using standard tools rather than factory replacement. Calibration procedures assumed that technicians would have minimal training and poor environmental conditions. Every aspect of the design accommodated the reality that equipment would be operated and maintained by ordinary soldiers under combat stress. German systems emphasized technical sophistication and assumed that specialist personnel would be available for operation and maintenance. Würzburg radars achieved excellent performance when properly calibrated by trained technicians operating under controlled conditions. But combat conditions were never controlled, and specialist personnel became casualties at rates that left equipment operated by inadequately trained replacements. The philosophical difference reflected broader contrasts between American industrial democracy and German technical aristocracy. American factories mass-produced equipment that worked adequately in the hands of common soldiers. German factories produced superior equipment that only specialists could employ effectively. When specialist casualties mounted and replacement training could not keep pace, German technical advantages evaporated, while American systems maintained consistent performance. Richter recognized these patterns with professional despair that bordered on intellectual betrayal. His entire career had been built on the assumption that German engineering represented the apex of technical achievement. Superior education, rigorous standards, and uncompromising precision created weapons that Allied forces could match only through overwhelming numerical superiority. The SCR-584 demonstrated that assumption was catastrophically false. American engineers had solved problems German specialists claimed were unsolvable. They had created equipment that outperformed German systems while requiring less maintenance and training. They had designed for real battlefield conditions rather than theoretical ideals, and that practical focus had produced weapons of devastating effectiveness. The strategic implications were inescapable. Germany lacked the industrial capacity to produce equivalent radar systems in quantities that would matter militarily. Retooling factories, retraining personnel, and redesigning doctrine would require years that the war would not provide. Even if equivalent technology could be developed, American production advantages would ensure that Allied forces deployed 10 systems for every German unit. The war's outcome had been determined not by courage or tactical skill, but by industrial capacity, married to engineering philosophy, that prioritized practical effectiveness over theoretical sophistication. German forces would continue fighting with dedication and professionalism, but they were fighting a war whose mathematics guaranteed their eventual defeat. December 1944 brought Germany's last desperate offensive through the Ardennes forest. American forces, caught off balance by the surprise attack, fell back under the weight of concentrated Wehrmacht armor and infantry. For 3 days, German advances penetrated Allied lines deeper than any enemy breakthrough since D-Day. Then, American artillery began firing with devastating precision that Wehrmacht commanders could not explain through conventional doctrine. Shells detonated at optimal heights above German positions, creating airbursts that shredded infantry formations and destroyed soft-skinned vehicles with systematic efficiency. The accuracy exceeded anything German forces had encountered during previous engagements. SCR-584 radars, originally deployed for anti-aircraft defense, had been adapted for ground fire control with results that transformed artillery effectiveness. The radar tracked shell trajectories in flight, allowing fire control officers to calculate precise impact points and adjust subsequent salvos for maximum effect. Counter-battery fire located German artillery positions within minutes of their first shots, directing devastating concentrations that destroyed entire batteries before they could displace. Near Bastogne, American batteries caught a Wehrmacht battalion attempting to cross the Sour River during daylight hours. The SCR-584 provided continuous tracking data that allowed the M9 director to calculate airburst heights with mathematical precision. 702 German soldiers died in minutes of coordinated fire that created a killing zone no infantry formation could survive. General George Patton's subsequent message to Ordnance Department officials became legendary among artillery crews. "The funny fuse won the Battle of the Bulge for us. When all armies get this shell, we will have to devise some new method of warfare." The proximity fuse he referenced had been married to SCR-584 fire control, creating a weapon system that rendered conventional infantry tactics suicidal. German prisoners reported that overhead bursting American shells created psychological terror unlike any weapon they had previously encountered. Wehrmacht doctrine provided effective countermeasures against conventional artillery. Dispersed formations, rapid movement, and protective terrain could minimize casualties from timed fuses that detonated at preset intervals. Proximity fuses, guided by radar fire control, rendered such tactics useless. The shells sensed ground proximity and detonated at optimal heights automatically. Radar tracking ensured that concentrations landed exactly where German forces were attempting to maneuver. The combination transformed American artillery from an area weapon requiring mass fires into a precision instrument capable of destroying point targets with individual salvos. By January 1945, German offensive capability had been shattered by the accumulated effectiveness of American fire control technology. Wehrmacht units that had advanced confidently during the initial phases of the Bulge offensive found themselves unable to move during daylight hours without triggering precisely coordinated airbursts that destroyed entire squads instantly. The psychological impact exceeded the physical casualties, though casualty rates were devastating enough. German soldiers understood that American artillery could kill what it could not see, transforming near misses into certain death. Movement meant detection. Detection meant precisely calculated fire. Fire meant casualties that German medical services could not treat and that troop replacements could not offset. Richter received updates on the Ardennes fighting through Wehrmacht intelligence channels. Each report confirmed what his technical evaluation had predicted months earlier. American fire control superiority was determining battlefield outcomes, regardless of German tactical skill or strategic planning. The mathematics of radar-directed weapons had created an asymmetry that conventional military doctrine could not overcome. The SCR-584's versatility particularly troubled German analysts. A system designed for anti-aircraft fire had been adapted for counter-battery operations, ground target tracking, and even coastal defense against small vessels. American forces were discovering new applications for their radar technology faster than German forces could develop countermeasures against existing threats. This adaptability reflected design philosophy that emphasized flexibility over specialized optimization. The SCR-584 provided accurate position data that could direct any weapon system capable of accepting electrical inputs. Anti-aircraft guns, field artillery, naval weapons, even searchlights and fighter direction could benefit from the same basic radar platform. Investment in one technology multiplied effectiveness across multiple tactical applications. German radar development had proceeded along specialized paths that limited cross-application potential. Würzburg systems were optimized for anti-aircraft fire control and fighter direction. Separate radar types served naval gunnery, coastal defense, and early warning functions. The specialized approach created equipment that worked well within narrow parameters, but could not be adapted easily to new missions as tactical requirements evolved. By war's end, over 1,700 SCR-584 systems had been produced and deployed across every theater where American forces operated. The radar's effectiveness extended beyond anti-aircraft applications to fundamentally reshape ground warfare through precision fire control that converted conventional artillery into a weapon of mathematical certainty. German forces continued fighting with professional skill and determination, but they were fighting against systematic advantages that individual excellence could not overcome. American fire control technology had transformed ordinary weapons into instruments of devastating precision through automation that eliminated human limitations from the tactical equation. Richter survived the war and spent his remaining years working in civilian telecommunications. He never spoke publicly about his technical evaluation of the SCR-584, but colleagues noted his absolute refusal to dismiss American engineering capabilities based on assumptions about European technical superiority. He had learned through bitter professional experience that practical effectiveness defeated theoretical sophistication when design philosophy emphasized battlefield reality over workshop ideals. The SCR-584 remained in service with American forces until the mid-1990s, upgraded repeatedly but retaining the basic design philosophy that had made it revolutionary in 1944. Its servo-driven antenna mount eventually served as the foundation for early tornado research radars, demonstrating that well-designed mechanical systems could remain useful for over half a century, despite revolutionary advances in electronics. The broader lessons extended beyond radar technology to fundamental questions about industrial philosophy and weapons design. American engineers had created equipment that ordinary soldiers could employ effectively under combat stress. They had prioritized reliability over complexity, adaptability over specialization, and practical effectiveness over theoretical performance. These choices had produced weapons systems that determined the war's outcome as surely as numerical superiority or strategic planning. German technical aristocracy had assumed that sophisticated equipment operated by specialists would defeat simpler systems manned by common soldiers. The assumption proved catastrophically false when specialist casualties mounted and training could not produce replacements fast enough. American industrial democracy had created weapons that maintained effectiveness regardless of operator skill level, allowing numerical advantages to compound into overwhelming tactical superiority. The mathematical transformation was complete. What had begun as a physicist's proposal for automatic tracking radar had evolved into a system that let artillery hit targets they couldn't even see. Darkness, weather, and evasive maneuvering no longer protected enemy forces from weapons whose accuracy was limited only by the precision of mathematical calculation and the speed of electronic response. German engineers who examined the captured SCR-584 had realized they were studying more than superior technology. They were confronting an entirely different philosophy of warfare, one where automation and mathematics had replaced human skill and tactical intuition as the primary determinants of combat effectiveness. The future of military technology would belong to nations that understood this transformation and designed their weapons accordingly. The radar dish that had seemed so ordinary when first examined at Kummersdorf represented the apex of wartime American engineering achievement. It embodied industrial capacity married to practical design philosophy, creating weapons that ordinary soldiers could employ with devastating effectiveness. The simplicity was deceptive. Behind the unassuming exterior lay mathematical precision that had reshaped warfare itself. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.